Okay, hello and welcome back to Chemistry Talk. Today, we'll be continuing our discussion of acids and bases, specifically weak acids and bases, and discussing how to calculate pH of weak acids and bases. In the previous video, we discussed four new terms: the Ka, the Kb, the pKa, and the pKb. We're going to need to be able to switch from these units in order to calculate the pH of weak acids and bases. So our first problem says that the pH of a weak acid, HX, is 6.2. The initial concentration of the acid is 0.01 molar. Calculate the Ka. So I've made up some acid here, HX, and it's a weak acid, which means that it's not going to dissociate 100%, so you're going to have an equilibrium concentration. You're going to get the hydrogen ions in the solution, and this X anion doesn't really matter because these concentrations will be the same. Also important to note, this is what we would call a monoprotic acid, meaning when it dissociates, it only has one proton. In this case, and in most cases with the acids, it's a hydrogen. So if I have a pH of 6.2, what I'm really interested in is the hydrogen ion concentration, because at equilibrium, that's the number that I'm going to gain on the right-hand side. I'm going to gain those hydrogen ions, and I'm going to lose that hydrogen ion on the reactant side. So what I'm really curious about is what that number is. And if you recall, the pH is equal to the negative log of the hydrogen ion concentration in a solution. So if we have the pH, but we're solving for the hydrogen ion concentration, we need to take the negative inverse log. And how you do that is you take 10 to the negative x. 10 to the x to cancel out the log, the negative to cancel out the negative sign. So when you do that, you get that the hydrogen ion concentration in this solution equals 6.3 times 10 to the third. So all I did was I took the inverse log of the hydrogen ion concentration, and then I made it the negative, and that canceled out the negative sign in front of the logarithm. It's actually 6.3 times 10 to the negative 7th. So 10 to the negative 6.2 gives us the hydrogen ion concentration. So what I'm going to do now is I'm going to write an equilibrium table. I'm going to calculate what my concentrations of undissociated acid and hydrogen ion is at equilibrium. From there, I can make a Ka expression to find the Ka of the acid. Initially, I'm starting out with the 0.01 molar of the acid, but I have no product initially. What am I reacting? Well, I'm going to lose the hydrogen ion on the reactant side, because I'm donating that, so I'm losing 6.3 times 10 to the negative third. But I'm going to gain that value on the product side. And I'm going to gain it twice for the hydrogen and the X anion. So rather than writing that twice, I'm just going to write this product squared. So at equilibrium, and that's what we care about really, how much reactant do I have? Well, I have 0.001 molar left of undissociated acid, and I have 6.31 times 10 to the negative third, 10 to the negative 7th squared of hydrogen ion and X anion. So from here, what I can do is write the Ka expression. The Ka expression is simply the equilibrium expression, products over reactants. In this case, our hydrogen ion concentration times the X anion divided by the undissociated weak acid. So we just found these numbers. On top we have 6.31 times 10 to the negative 7th squared, because there's two of them. On the bottom we have the undissociated acid, 0.001 molar. So when you do that division, you find the Ka of this weak monoprotic acid to be 3.98 times 10 to the negative 11th. And that's the final answer. So what we did is we took the pH, we found the hydrogen ion concentration, that's what we're reacting. We found our equilibrium concentrations, and we plugged that into the Ka equilibrium expression. Okay, the acid present in milk is lactic acid, it's a weak acid. If the Ka of lactic acid is 1.38 times 10 to the negative 4, provide the following: the pKa of lactic acid, the Kb and pKb of the conjugate base, and the percent ionization of a 0.5 molar lactic acid solution. Well, the first thing I'm going to do here is write the dissociation of the acid. It is lactic acid, CH3, CH, HC3, H5O3. You don't need to include the water because it's a weak acid. You only need to include the water for a weak base. The conjugate base of lactic acid will lose one hydrogen ion, so it would be C3H5O3 with a minus charge. It lost a proton, plus that extra hydrogen ion in the solution. Sometimes chemists will represent weak acids by writing a hydrogen ion and the acid. So I could have abbreviated this as HLAC for lactic acid, but I'm going to write out the full formula. Important to note here, this is the acid base conjugate pair. I'm going to write conjugate pair. You have the lactic acid, and the conjugate base of the lactic acid is the C3H5O3 minus ion. It lost the hydrogen. That's the difference between the acid and the conjugate base. Now for the questions. What's the pK of lactic acid? Well, the pKa equals the negative log of the Ka. We're given the Ka of the acid. The negative log of 1.38 times 10 to the negative 4th gives us a Ka of 3.86. Rewrite that, actually. So like I said, the pK equals negative log of the Ka. So the negative log of 1.38 times 10 to the negative 4th, we get the Ka, rather the pKa, to be 3.86. Now this is a helpful number because now I can find the pKb, and that's what it's asking, the pKb of its conjugate base. The pKb would equal 14 minus the pKa. The pKa here is 3.86. So the pKb would equal 10.14. Now at this point, I have an option. To find the Kb, I could use the Ka and the water dissociation constant Kw to solve for the Kb. Or I could use the fact that the pKb equals the negative log of the Kb. And since we know the pKb, we're solving for the Kb. So we would take the negative inverse of the pKb. So the Kb would equal 7.24 times 10 to the negative 11th. So what I did was I took the inverse negative log of the pKb. I could have also solved for this by saying that the Ka times the Kb equals Kw, which is a constant. And I could have solved for it that way, but I chose to solve for it this way. Okay, final thing we're asked for is the percent ionization of a 0.5 molar lactic acid solution. Well, in order to do this, we're going to need to find the equilibrium expression. We know the Ka. We can solve for the concentration of the hydrogen ion at the equilibrium, and we can then use that to solve for the percent ionization. So I'm going to write a table here. The table is going to correspond with the equation up here. So going from left to right, we're starting out with 0.5 molar of lactic acid. I don't have any product at this point. What am I reacting? Well, I'm going to lose X on the reactant side. I'm going to lose that proton, but I'm going to gain it on the product side. So what is my equilibrium concentration? Well, if I'm looking for X, it would be 0.5 minus X for the reactant side, and it would be X squared for the product side. I know the Ka of the lactic acid, so I could say that the Ka is equal to X squared over 0.5 minus X. Now there is a little bit of a problem here because X is in the denominator, which means to bring it up, I would have a quadratic term and it would make it a little bit messy. But since the Ka is greater than 10 to the negative third, we can eliminate the X in the denominator. That's just a rule. So we can solve for X. We can solve for the numerator's X by eliminating this bottom. So we would say that the Ka of lactic acid, 1.38 times 10 to the negative fourth equals X squared over 0.5. We eliminated that X. So X comes out to be 8.31 times 10 to the negative third. Now this, since X is our hydrogen ion concentration, this is also equal to the concentration of hydrogen ions at equilibrium. So the percent ionization would equal the hydrogen ion concentration, which we just found, 8.31 times 10 to the negative third, divided by the molarity of the acid, 0.5 molar. So we get the percent ionization to be 1.6%. I hope this helped you to understand how to calculate the pH of weak acids and bases. In future videos, we'll discuss the pH of acidic and basic salts and buffer solutions.